Hey everybody, this is Larry. This is me doing week 4 of the Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this one. Today we have a hard problem. So hopefully it's not too hard. I'm ready to take a nap. Maybe I should have taken a nap. So let's see how it goes. We have 2371 minimize maximum value in a grid. You're given I still got all by C. All by C integer matrix grid containing distinct positive integers. You have to replace each integer in the matrix with a positive integer satisfying the following condition. The relative order of every two elements that are in the same row or column should stay the same after replacement. The maximum number in the matrix after replacement should be as small as possible. Okay. Yeah, I mean, I think there are a couple of ways to think about this. First, it's just kind of make sure the constraints are okay. It's 1,000 by 1,000, which is a lot of elements, but you're also constrained by this, so you're okay. You just have to make sure that you're a little bit reasonable. But the key thing I think for this one is going to be noticing that this is a graph problem. I think that's the first thing to notice. And the way that I would think about it is that this is you're trying to impose order, right? And in order, you could say that 2 is less than 5, or maybe 2 is before 5, or something like this, right? For example, in this one, and you could kind of write, okay, the examples are kind of terrible, but for example, let's say maybe this is the matrix that they give you, but let's say we just add a few more numbers, right? So maybe you have like 6, I don't know, 7, I don't know, 2, and then 8, and then maybe a dupe, right? Another 2, right? I guess we need one more number here. And the idea here is that we just kind of impose a graph. In this row, there's going to be 2 is equal to 2 is less than 5, less than 7, less than 8, right? And in a partial ordering graph, if you will, then now you get 2 is connected to 5, and 2 is connected to 7 because of transitive property, and 2 is less than 8, and you can kind of connect a directed graph in that way, right? Whichever way, I guess it doesn't matter. And as a result, after you kind of draw this graph out, you realize that what you actually want to do is a topological sort, or maybe you even think of it as a greedy, which it's fine, because then you just basically try the smallest number that you can do. And the smallest number is going to be, the smallest number is just going to be, another way, let me rephrase that. Every number you're going to try to do is going to be the smallest number that you can do at that point. So then you just kind of keep going, right? And make with that assumption. So, okay. So I think that's really generally the idea for this problem, and then it's just about sorting out the ordering. Of course, there's going to be a lot of numbers, right? 10 to the 5th at most, so you can't really create the entire graph, because, for example, if you have, are they all unique? Oh, they are actually distinct, so actually I lied on this one. But even without that, with or without that, I don't know that it matters that much, honestly. But right, whatever. But still, my point is that n square, even on just like one thing, n square graph is going to be too expensive, right? Because n square is just too high. But because this is a partial order thing, right? There is the transitive property. All you have to do is sort them in a good way, and then as long as we get the small, like, we don't need to know anything other than the smallest number, right? And I think that's the key part about it. Because if you think about it, even just like what I wrote out, instead of writing 2 is less than 7, we can infer that from 2 is less than 5 and 5 is less than 7, and then transitive property. And if you kind of just think about it as a DAG, right, and then now you have a topological sort, there's a lot of implications going on, right? Like if we remove 2, then because it is a total ordering, everything that's smaller than 5 is also going to be smaller than 7, for example, almost like in a dominating kind of way. So you don't need the entire thing. Okay, I think that's really the idea. And then it's just about data structure and setting it up so that we make sure that we go really fast, right? Okay, so here maybe we want to go each. It doesn't really matter, but we can just do things at a time, right? Yeah. So then we can just do like each row at a time. Right? How do I want to write this? I'm still kind of debating in my head, honestly. So we have xy, right, and then the value, right? So grid of xy just for value, and then now I know that I want to sort, and it's unique anyway, so that's fine. So I'm going to grab a drink real quick. A little bit thirsty. Okay. Yeah. And yeah, I mean, I think you can also do this maybe with whatchamacallit, union find or something, but I'm not gonna bother. But now that we're sorted, we can maybe even just go. How do I want to write this? Right. Now that it's sorted, we can say, yeah, all we have to do is just figure out how many dependencies are there in that row, right? And also be able to service the next number in a good way, right? I mean, of course, if you recall the vanilla topological sort algorithm, you could, you know, the lazy, easy, naive way of writing it is that, okay, you every time some dependency goes to 0, then like if nothing depends on it, then now you kind of free it up to do, right? So we can maybe do something like like maybe we can do a lookup is kind of weird to say, but okay, yeah, maybe a next row, something like this. So or row next is equal to right? So is equal to say none, right, times c for right. So we just create a r times c row next, and we'll do, for symmetry reasons, we'll do collex. But basically, it is saying that yeah, row of next of xy is the next item that or the next cell that is on this row, right? Something like this, and the same for columns. So then now after we sort it, we can do something like yeah, we can do row next. Sorry. Now we want to go through it for y in range of c, and of course there are c elements in row, right? So yeah, so row of, and we go to c minus 1 because the last element we don't need to do it. Row next of xy is equal to row of y plus 1. So that will give us this thing, and then we just kind of get the xy, right? Oh, we could just do it this way. I mean, I guess maybe we could also just store this, and just because this is easier to write, right? And that's really the idea for this. Is that okay? Now for each item, we go, okay, what do we relax and relax in the graph term? The next node, right? Okay. And then we do the same for columns, right? So right. Oops. Set this up. And keeping in mind that, well, I mean, all the numbers are distinct, so we don't have to worry about tiebreakers, which is kind of nice, I suppose. I could have sworn that there is a variation of just that. Yeah. Oh, jeez, Larry. that doesn't worry about, but maybe I'm wrong on this one. Oops. Right. So then now, and maybe one more thing that we can do is just dep is equal to 0 times c for and it just shows that how many things depend on this, right? And here maybe we can write in a backwards way, y plus 1, the xy there, so the first element, or maybe we can even do right, something like this, or maybe not xy, but next y, right? So it's equal to this, right? And then now dependency of increment by 1, right? And we do the same idea here for columns, but a loss of generality, right? And then now all we have to do is, and we set up the for a topological sort, we can just do the topological sort, right? And it is just, you know, what it's going to look like. We have a queue, or the way that I'm going to do it is with queue. I do wonder if you can do it top down, but I'm going to do it bottom up, or just with a queue with topological sort, right? So then if this is the case, if depth of xy is equal to 0, then q dot append xy, right? That's really it. We kick it off, and then now while length of q is greater than 0, we have xy is equal to q dot pop left. So then now, okay, so this is now, remember, all these numbers will have to be the smallest number, and we do them all at the same time. And also, because they're all unique, it is impossible for two numbers on the same row to have the same priority. So therefore, you want to get the smallest number that is possible. So okay, so there are two things more we have to set up. One is just the answer, right? I mean, that's just what we want to return. So, you know. And then the other is the smallest value, which is the next thing. Here, right, or maybe row min is equal to 0 times r, and col min is equal to 0 times c. And the reason here is just that it keeps track of the next number that is available for that row, because that row can only increase, right? And why that is important is that they don't show you a case here, but for example, maybe you can draw a graph such that it is going to be 1, 2, 3, 4, maybe 2, 3, 4, and then this is going to be 5, right? Even though if you look at it by or maybe this is not a great example, but like maybe 6, and you know, I don't know, there's some like thing here, and as a result this is going to be 7, even though 4 going to 7, that, you know, makes sense or whatever. So there are stuff like that where it's not like it just doesn't go up by 1, right? They can jump up a lot, though they don't show it. But yeah, okay, so now we know that this is the smallest number in the row and column because it's the smallest number on the board right now. Or by smallest I mean yeah, I guess I do mean smallest, right? And then we can reduce this by, yeah, new value is going to be equal to row min of xy or x, and then max of this and col min of y, right? So that's the biggest number that's currently on the row. So we're going to add 1 to get the next number, and then we just set it to and that's pretty much it. We want to update min to ny, and col min y is equal to ny, and that's pretty much it, I think. I hope. Let's give it a quick spin. Hope I didn't do anything silly. I mean, this is clearly wrong. Okay, so we have a no. That means that we don't pop. Oh, I'm just being dumb, because here this is good, but then now you have to relax the dependency on the other ones, right? So then now that's why I did all these things. I don't know. I'm just kind of a silly boy today. But yeah, so okay. So if row next of xy, so there is a next row element, right? If this is not none, that means that there is an element, right? And what is that element? that element is going to be this nx thing, right? You got a row next of xy, and then yeah, and then we just want to say, okay, look, friend, all we're saying is we subtract 1. But then now, if this is equal to 0, then that means that now it's eligible to be 3, right? So that is basically the idea. Yeah, and then we do it the same for column. And that's pretty much it. Hopefully. Oh, nows. That's weird. So 3. Don't know what. Tell me. Do we miss popping something? Let's see. And it doesn't do 0, 0. I mean, this is from the second one, that's why. But Alright, I mean, we can just look at the dependency every time because I'm lazy. Okay, so 3 depends on 1 and 2, so that's why there's 2 elements, right? Did I get the columns one? I did some copy and paste, so it's possible that, you know, I've done some silliness. Next row, I mean, I think that makes sense, right? Maybe, hopefully. Because okay, so the first number is that we care about. It's gonna be one of the ones. I don't know which one, but that's fine. Right. Yeah, but that's already wrong. It should be 1, 0. So I guess it matters which one, just so that we know which one we're debugging. Oh. I mean, I suspect it's just a typo, so I'm not really that worried, but I am tired and sad. Okay, so 0, so the first one is going to be 0, 1, so the one in the upper right corner. So it does get rid of the thing, but it doesn't, it looks at 1, 1, but this part is wrong. So call next is none. Is this right? Am I right? I don't know, that's wild. I mean, I don't know. It is what it is. I probably have a typo somewhere, but yeah. So 0, 1, we have none on the row next. So maybe I was looking at the wrong code. Okay, so maybe row we're having some issues. X, Y. So this first row we saw it, right? I mean, it did a plus minus plus equal to 1, so that means that this should be doing something, right? Oh, I am dumb. This is wrong. It's not XY. Okay, because the XY is wrong. It is not. It is the value of the thing at. Yeah. Okay. So it should be like maybe CXCY is equal to row of Y, right? And then now this is what I mean. Okay, so I'm just being dumb. And the same idea here, except for with com and x. Right. Silly mistakes. Oh, yeah, right. Also, this is why copy and paste is bad. You have to put code changes in 2 places every time you do. But yeah, just a very silly, what did I do even? I already forgot. Oh yeah, I confused X, Y, and things. There's still some printing. Oh, right here. So yeah, looks okay. Let's give a quick submit. Silly mistake aside, hopefully this is good, and we are good. We are Gucci, and we are done with the weekly. Was this a contest problem? Probably, I guess, maybe, I don't know. But yeah, so where's the complexity here, right? Well, we look at each cell at most once, so that's pretty good. We do have sorting though, right? So it's gonna be n log n, a lot of n log n things, right? Or maybe sub. Like it's not. Oh, excuse me. Like it's not all of the sorting, but I guess in the worst case it would be because you have, if all of them are, if all your items are in one row or one column, then the sorting is just gonna be n log n, right? So I guess that's the worst case. And yeah, and everything else is linear or constant and amortized over time. And that's all I have with this one. Yeah, let me know what you think. Ooh, wrong button. Let me know what you think. Thanks for watching. And yeah, let me show you the top and the bottom. And I think we're good. I'm curious how I did last time. Is it the same idea? Wow. I did it way cleaner last time. I guess I didn't think about... I didn't even need to do topological sort on this one. I just kind of went like, well, oh, because it's unique. The reason why I did it my way is because I think even though I knew it was unique and we talked about it, my first instinct was to solve the one that is not unique. And as a result, and technically I did it wrong if that's the case, but I had the structure so that I was able to solve that. But because everything is unique, you're just going to go do them in order, and then now you're just compressing it down, and that's why. So I feel kind of dumb, but it's still the same complexity, I think, because it's just the sorting, right? It's just that, yeah. And in fact, I think my code is slightly faster, I guess, and it shows up here, because the other one is going to be a hard n log n for every space, but where here we only sort on the columns or the row per item or something. Anyway, that is all I have with this one. Let me know what you think. I'm a little rushing it because I need to take a nap. Yeah, stay good, stay healthy, good mental health. I'll see y'all later and take care. Bye bye.